Good afternoon, everyone. Welcome to the fourth class of Reagents in Organic Synthesis. First of all, happy Janmashtami. So now we are going to start the class. So first we will discuss about some reducing agent. First we are going to discuss about dival H reduction. So dival H is nothing but diisobutyl aluminum hydride. So it has this butyl group which are in dimeric form, and this hydryl group are coordinated with the two aluminum center which is in dimer form. So dival H is mildly reducing agents. It mostly occur reduction into low temperature. So generally ester and nitrile group under dival reduction condition forming aldehyde. So first this reaction happen in low temperature at minus 78 degrees centigrade. In high temperature or room temperature, it doesn't form aldehyde, it forms alcohol. As well as the equivalency of dival also important for the dival hydride reduction. So if we use one equivalent or 1.2 equivalent of dival in any kind of reductions of ester or nitrile, it will form aldehyde. More than one equivalent or two equivalent or three equivalent of dival give the alcohol. Uh, so dival, the aluminum in this hydride formation are somewhat Lewis acidic. So the mechanism of the dival hydride reduction. So first, this aluminum as a behavior of Lewis acidic. So due to this Lewis acidic behavior of this aluminum, so the lone pair of the oxygen react with the aluminum and form this deuterionic intermediate. Now the hydride is transferred to the carbonyl center and form this hemiacetal, which is coordinated to aluminum. So why this reaction happen in low temperature? So now this hemiacetal, as we all know, what is acetal. So aldehyde in presence of this reaction condition plus from this is called acetal, hemiacetal or acetal. So hemiacetal. Perhaps if this this is in presence of ketone, this called as ketal. So we all know that. Now, what happened in that at low temperature, this hemiacetal is stabilized. The oxygen aluminum complex is stabilized. Now, further under workup, the O aluminum bond breaks and is like this way. So this will go, this O aluminum bond breaks and methanol will remove. So which gives aldehyde. And the side product is this. Now the mechanism of the aldehyde formation of nitrile in rival H condition is there. So as aluminum is metal or it has a Lewis acidic behavior, so nitrogen or lone pair of the cyano group activated this and form this and nitrogen aluminum complex. Now this hydride is transferred and form this imine. So now this imine under hydrolysis form aldehyde. So now we are going to discuss about Wolff-Kishner reduction. So any kind of aldehyde or ketone from alkane, that reaction is called Wolff-Kishner reaction. It is uses hydrogen. So NH2 NH2, that is hydrogen. Hydrogen and Ku is very strong base under basic condition, and ethylene glycol at a high temperature 180 degree to 200 degree centigrade, it form this kind of alkane under reduction, with crystal reduction. So what is the mechanism? So first, any kind of aldehyde or ketone under hydrogen or any kind of amine, aldehyde in presence of amine from imine. So this is as this is imine, but this is called hydrazone. Just so this is called hydrazone. So now what happened? The base will abstract proton from the ethylene glycol, which abstract proton from the amine. So which is forming this negative charge on the nitrogen center. This will now this will go like this way, and from this anion, now this anion abstract proton from the ethylene glycol and protonated, and from this dinitrogen compound diamide. Now this proton, as nitrogen has proton, this proton is first further abstracted by the base or ethylene glycol oxide. So which is forming this. Now this will go and nitrogen will lose. So this is the driving force of this reaction, removal of nitrogen. So removal of nitrogen increase the entropy of the system. So due to the increase of entropy, the reaction is proceed further. So this is the driving force of the reaction. So now this negative charges will form after denitration. Nitrogen will remove, and now this will protonated in presence of any protic solvent or proton source, give this kind of alkane and nitrogen as a side product. So this is a very important reaction. So by this way, we can remove any kind of ketone or from a system and form fully alkane or compound containing compound. So this is the modification of Wolff-Preston reaction. So this is Shapiro reaction is a very important reaction. So any kind of aldehyde or ketone. So this under tosyl hydrogen. So under tosyl hydrogen. So this after removal of water from this tosyl hydrogen. Now if we take very strong base such as N-butyl lithium. So this is a strong base. So butyl minus lithium plus. So now what happened? This NH is acidic, and this is also this proton here, two proton are available. Both the proton are acidic. So what happened? The butyl group abstract these two proton as two equivalent of butyl lithium we are using, and form this this will abstract and form this kind of negatively charged compound. SO2R. This and these two negative charge compound will form. Now as it is negatively charged, the cation is lithium, so it can stay like this way, lithium plus. Now the negative charge and ion will push its electron to this way, and this double bond will move and leaving this tosyl group. So this will remove as a paratoluene sulfonic acid. this, and after that what happens? After removal, this will form. So now this negative charge will go and form after elimination of nitrogen. So here also the driving force is the elimination of nitrogen from this lithiated compound. Now this lithiated compound in presence of any kind of electrolyte, here we are using water as after water it is formed alkene, any methyl, so it will form methyl containing compound. Any kind of electrophile it can be trapped by this lithiated compound methyl. So if we use DMF, so DMF is a formylating agent, so it formyl group will be forming. So CHO, that is the formyl group, or any kind of RX. So here it will be substituted as a. This is a very important reaction. So any kind of ketone which has alpha proton present in the system under tosyl hydrogen and two equivalent of strong gas such as butyl lithium forming this alkene compound. This called reaction is called as Sapiro. Sorry, some technical glitch happened. So this is called Sapiro reaction. So something same reaction that is called Bamford-Stephen reaction. So in the previous reaction, what happened? Very strong base has been used to abstract proton. So here in this Bamford-Stevens reaction, little bit of mild base such as sodium methoxide, sodium, this kind of base is used. Uh, Sodium containing base or potassium containing base is used uh, in equivalent amount. So if what happened in this reaction, here alkene has been formed. So here alkene has been formed. What is the mechanism we can discuss? So what happened in the first case as how we prepare this one. So this ketone under tosyl hydrogen, tosyl NH2 from tosyl hydrogen. So any kind of ketone from tosyl hydrogen under tosyl hydrogen reaction condition. Now what happened? In presence of base such as sodium methoxide. So now this base Na plus OMe minus. So now this base abstract proton from the nitrogen center and from this negatively charged compound. And as this nitrogen has lone pair, so it will go via this and minus tosyl remove tosyl as a leaving group, it will remove. So and from this diazo compound. So here is a two type of possibility are there in presence of protic solvent such as ethanol, which has which can donate its hydrogen through hydrogen bonding, ethanol, methanol, butanol. So these are protic solvent and aprotic solvents such as toluene, DCl. So these are aprotic solvent. So now what happened in presence of protic solvent? So this nitrogen negative charge will goes and this will abstract proton from the protic solvent, and from this nitrogen carbonium through carbonium mechanism. So and after the elimination of nitrogen, it will form this electrophile, that carbocation, and after the neutralization, this is from this kind of alkene. So this is under protic solvent. So in presence of protic solvent where we have hydrogen, so it will go through carbonium mechanism. But in presence of protic solvents toluene the same, so it will go through carbon mechanism. So this nitrogen push is this negative charge pushes electron and from this carbonium. Now removal of nitrogen give this carbon. Now this carbon, if it has hydrogen, so hydrogen will go there and from this double bond. If there is no hydrogen, so such as R1, R2, R3, R. If any compound has no hydrogen, so what happen in this case? The group which has there, it will migrate. So it migrate like this way, and from negative charge, I am migrating R2, R3 and R4 will be same. As is it migrate, so it will form positively charged, and if here migration happen in this center, it will form negative charge. Now this positive negative charge will form a double bond here. R1, this is R2, R4, R3. So if any compound has no hydrogen, or it is more compound which is which has any kind of alkene, aromatic or aliphatic group here in spite of hydrogen, that will go or that will migrate. So this reaction is called Bamford-Stevens reaction. Now we are discuss about one example of Shapiro-Bamford reaction. So here what happened is there, this hydrogen of camphor, this is camphor which has been prepared through the this ketone, which under methyl hydrogen or presence of little bit of acid, catalytic amount from this hydrogen. Now, in presence of Shapiro condition, such as in butyl lithium to equivalent, it forms these two boron, and in presence of sodium methylene glycol, that is a backward Stephen reaction condition, it forms camphene. So what happened is there? What is the mechanism why it giving two different product? So as n-butyl lithium is very strong base, so under Shapiro, it can abstract what happened is there. Now as n-butyl lithium is very strong base, so it can abstract this proton and butyl group and form a negative charge here after abstraction of proton. This now what happened in there? This will go and tosyl will remove, which will form this one. Now this will go, and after elimination of nitrogen, this negative charge is formed, which after abstraction of proton from solvent or tosyl hydride, which has removed from the system from this two bonding, this one. But in case of sodium condition, so what happened in this case? So as sodium in presence of ethylene glycol from sodium ethoxide Na plus, so O minus. This is the this will come under sodium. So this is a not that much of strong acid which abstract proton. Sorry, that much of strong base which abstract proton from this center. So it will proton abstract proton from the nitrogen and from this one. Now this will go and this double bond will migrate, which form sorry, I'm cleaning this one. So this negative charge as nitrogen has lone pair, so it will go and as nitrogen has lone pair. So this lone pair of nitrogen puts the electron cloud here and tosyl group will remove, which form this one. Now under aprotic solvent, so this nitrogen will remove as a nitrogen gas and from the carbene here, this carbene will now what happen is there, this carbon has no proton. As I previously discussed, the Danforth-Stevens reaction, if there is proton, that will migrate, but here there is no proton. So this CC single bond will migrate here. I'm cleaning this one. So, writing this. Now what happens is there, this will come this one bond is forming here directly. This is the methyl and this is this two methyl. So as it broke from the methyl side, so it broken from this side, so it will form positively charged and it will form negative charged. After that, this methyl has proton This is connected. So this methyl has proton. So this will attracted by this one and this will go and form a double bond. So what happens? Methyl, one methyl. This is the double bond. This is the 2 methyl. Now, if we flip the structure, it will form like this. So this is the difference between Bamford and Shapiro reaction. So in presence of Shapiro reaction, very strong base such as N-butyl lithium is used, which form alkene. But in case of Bamford reaction, it is also called alkene, but it goes through carbenium or carbene mechanism. But in the case of Shapiro reaction, it goes through carbenium mechanism. Both are called alkene, but one is case we using very strong base, one is case we using milder base. So now we will discuss about the reduction through boron reagent. So boron is a triclonal planar compound and valence electron is 6, 1p orbital is empty. So that's why it formed dimer and to fulfill its octet. So it remain in the dimeric form D2H6. Also, in presence of Lewis acid, so as in presence of Lewis base, as it has a vacant p orbital, so it can accommodate any kind of lone pair of electron in its vacant p orbital. So it behave as a Lewis acid in presence of Lewis base. So in presence of Lewis base, such as lithyl, ether, THF, dimethyl sulfide, it form this kind of coordinated compounds. So it remain in the reaction mixture. So now what happened in case boron reduction? So in presence of any kind of alkene, so this is most this kind of alkene here, the two carbon is substituted by R1 R2, but in this case this two carbon is this carbon is free. So what happened is boron cases, so it appear in cis manner or hydrobolation happen in the cis orientation. So and boron this alkene react with the boron which has a least substituted carbon. So it react through anti-Markovnikov fashion. Anti-Markovnikov fashion. So it react through anti-Markovnikov fashion and transfer it hydride from this kind of organoboron reagent which come through syn addition. So the boron react with that carbon which is less substituted or sterically more facile. No steric kindred will be there. So this will react under anti-Markovnikov fashion and under H2O2 it will that boron react and form this alcohol. Now we'll discuss about Corey-Boxy-Shibata reduction. So this is the reagent which chiral reagent which has been used in Corey-Boxy-Shibata reduction. So any kind of ketone or aldehyde under BH3, THC or BH3 Me2S dimethyl sulfide combination reduced to alcohol under this kind of active catalyst. So what happened in this case? So this active catalyst under boron, so as nitrogen has lone pair and BH3 has vacant p orbital, so it can act as a Lewis acid. Lewis acid base pair it will form. So Lewis acid Lewis base pair it will form. Now this is also boron, so it also has a vacant p orbital. So now ketone or come in this center and the hydride will transfer from the boron and it will form this after elimination of the active catalyst. It will form this boron and after water it will form the alcohol. So this is the path one. In path two, what happens there? One equivalent of more BH3 can come and it will form this kind of diboron hydride complex, which under elimination can form this alcohol. So this is the important reaction which is called Kure-Boxy-Shibata reaction in presence of boron. So these are the useful behavior of Kore-Boxy-Shibata reagent. So we can prepare this kind of natural product in by Kure-Boxy-Shibata reagent. So this is active catalyst and this BH3-DMS complex selectively reduce this ketone. They are also this ketone are selectively reduced to alcohol and under tosyl or paratoluene sulfonic acid. So water elimination happening and giving this double bond. So I think this is clear. This is the basic reagent system we can discuss. First, Kure-Boxy-Shibata reagent is the main reagent used in boron reduction. So I have discussed. Now we will go to the problem solving class. First question is this one. So under ethyl aluminum sulfide at minus 70 degrees centigrade, then they have used diamond H. So what happens there between carbonyl and aldehyde? This is the carbonyl one, and this is aldehyde. Between these two, aldehyde is more electrophilic. It's more electrophilic. So now what happened as ethyl aluminum diethyl aluminum sulfide is a Lewis acid. So diethyl aluminum sulfide. So aluminum center is Lewis acidic. So now what happened as between these two, as yeah, electrophilicity of aldehyde is much greater than the carbonyl. So this aldehyde oxygen will react with the aluminum center as it is electrophilic in nature or Lewis acidic in nature and remove this SPH minus. Then what it will form? This oxonium ion will form now as it is more electrophilic. The removed is sulfoxide will react and utilize this oxonium, which form this one, aluminum, dimethyl, and SPH, sulfur. Now they have used dival H at minus 70 degrees centigrade. Between this ketone and aldehyde, the aldehyde is masked by the sulfide, diethyl aluminum sulfide. Now under dival H reaction condition, That hydride will react with the ketone and reduce the ketone to alcohol. Now what happens? So aluminum H2 will form after dimer H reduction. This pH to aluminum. It, after workup, it will give this product. So what? So if I briefly discuss is, so first what happened is this case due to the presence of this diethyl aluminum sulfide Lewis acid, this more electrophilic aldehyde is masked and the dimer H reduce the ketone. So this will be the right answer. So now the next question is this tosyl hydrogen in presence of butyl lithium 2 equivalent. So previously we have discussed so this is an example of Shapiro reaction. So what happens is this is how this alkene is formed. So as it is a very strong base, it abstracts this proton and this proton. It will form this negative charge and this negative charge. So now this will go. Oh, so if I write properly, n minus Pn, this this will go. This will go and remove tosyl. The double bond will come here. This now this nitrogen pushes electron and this methyl group is here and remove nitrogen. Nitrogen gas will remove or liberate, which give this anion, carbon ion, which will neutralize by solvent water treatment and form this alkene. So this is the example of Shapiro reaction. So now the next question is this. So carbonyl is completely saturated to hydrocarbon. So this is can be done through Wolff-Kishner reduction or Clemmensen reduction. So in Wolff-Kishner reduction, that is I have already discussed. This is a basic reduction. So one hydrogen KOH or dichrome or ethylene glycol, ethylene glycol has been used. So if we discuss about the mechanism, so what happened in this case is carbonyl under the hydrogen from the hydrogen complex. So this will form now as the nitrogen has proton, so the base will abstract this proton one of the hydrogen and it will go like this way. So this carbon anion is formed nitrogen double one N minus. Now this negative charge will come and this will be abstract fast proton, and the second negative charge will form and neutralize this system after elimination of nitrogen. So this carbon ion is formed with abstract proton, which gives the completely hydrogenated product. This cyclohexane will form. So this is the whole crystal reduction. So Clemenson reduction also a basic reduction. The amalgam has been used for the Clemenson reaction. So in this case also carbonyl completely reduced to alkane or saturated compounds. So now if we come the next question, this. So what happened in this case? So there are two type of carbonyl. One is the ketone and one is the this is ketone. This is allylic ketone. So between ketone and this allylic ketone is more electrophilic as this can this can resonating due to this resonating structure it will stabilize. So due to that it is more electrophilic. So between these two, if we treated this compound with tosyl hydrogen, so this will react fast between these two. So what happened in this case if we treated this as a as tosyl hydrogen, what happened? This will remain as such OSC double bond N NH TS. Now under acidic condition, so this imine form iminium and through sodium borohydride reaction, so under sodium borohydride, so hydride, sorry, sodium cyanoborohydride. So sodium cyanoborohydride is famous for reduction of the iminium. So hydroamination happen to neutralize this and form this one. OSC hydride properly. Swan, OSC, ketone, and here this amine will come. Now what happened? This NH bond will push its electron to here and remove this tosyl, which will give this compound N double bond N. Now there is a possibility of liberation of nitrogen. Nitrogen will be removed and giving minus elimination of nitrogen will form this carbon ion. Now this carbon ion will go like this way and epimerize this double bond. So the double bond can be isomerized. This negative charge will form through its abstract proton, and from this. So the right answer will be option B. So first, under tosyl hydrogen, the allylic alcohol, allylic ketone will react, and after elimination of nitrogen and isomerization of the double bond, it forms this product. So the next question, I'm erasing this one. The next question is the old Krishna reduction. So first stated with hydrogen and then KOH is diethylene glycol. So this ketone in presence of hydrogen from hydrazone. Now as this as diethylene or ethylene KOH can abstract this proton and form this negative charge. So we give this one. Now this negative charge will migrate here and this double bond will migrate. Give this one. Now this negative here form negative. This negative charge will abstract proton from the ethylene glycol and protonated. Further abstraction of this proton through the base. So this will abstract and nitrogen will eliminate and form this carbon ion. So after elimination of nitrogen with this one. So now what happens is this case as chloride is a good leaving group or moderate leaving group. So this negative charge will come and leave chloride minus as a HCl gas. So it will form this one. So the right answer is option D. So what happens is that first with crystal reduction following by removal of HCl, giving this product, the alkene. Next question is reduction through Boden. So what happened in these cases? There, so Boden can reduce ketone or ester to alcohol or acid to alcohol. So there are two type of alcohol is there. This was the alpha hydroxy alcohol. So if we come from this ester, this is the alpha hydroxy. So in presence of alpha hydroxy alcohol, Boden can form a five-membered stable complex, but not with the beta hydroxy alcohol. If we count is this, sorry, this is the alpha position, this is beta position, and in this come ester, this one is the alpha, this is the beta. So what happens is this case BH 2H. So boron, this hydroxy group will react with the boron and this hydride will transfer to the ester moiety and form this five member heterocycle, boron heterocycle. So due to this stable boron heterocycle, so this ester will reduce, not this ester. So now what happen in these cases? This will go and um, this will further as NMDH4 is catalytic ion of they have used or boron further reduce this aldehyde to alcohol. OBH2, OBH2. After hydrolysis, we will get this alcohol. So this is due to this formation of five member boron heterocycle, which is stabilized through alpha hydroxy group. So that's why this ester is alpha hydroxy ester is reduced, not the beta hydroxy ester. Now the next is the alkyl boron. So, so the structure of alkyl boron is this one. This is the alpine group. So this is the alpine boron. So, so what happened in these cases? So the reduction happened through the depends on the geometry of this boron. So it is in alpha form. Alpha form. So this boron in the alpha position. So the compounds which has, so this is the racemic, so it has two form. This is the alpha one, this is the beta one. Sorry, I have taken it wrong. So this is the beta one. So there is a there the possibility is that the alpha form only react with the alpha form. So the match and mismatch chemistry happen is if it is in the beta, this isopropyl group is the alpha form, then a reduction happen. So this hydride will transfer. But in these cases, the alpha form is matched with the alpha kinine. So that's why reduction happen to the alpha form, not with the beta form. So that can be explained through the cyclic transition state, but I am not explaining that. So match and mismatch chemistry we can discuss. So if it is in the alpha form and that boron also in the alpha form, that is the same plane. So we all know that boron transport is hydride on the same fashion. So that's why we are getting this product early. So the reduction of this ketone happen to only in this substrate which has the alpha orientation. So now there's a two possibility. The hydride will transfer from the alpha phase as sp2 center. The ketone is sp2 center. So it will come to the alpha phase or to the beta phase. So it is the hydride will, if hydride will come to the alpha phase, this will the alcohol go to the beta, or hydride come to the alpha phase, beta phase, the alcohol goes to the alpha. So both the possibility are there. So that's why the right answer is this one. So as the match chemistry giving the product as alpha, alpine boron has the alpha orientation. So the reaction happens through the alpha phase and giving this. So this reduced alcohol. So the ketone has sp2 center. So the hydride of the hydride of the boron come from the alpha phase or beta phase. So both diastereomer will be formed. So the major diastereomer and minor diastereomer ratio will be vary, depends on the substrate to substrate, but both the isomer will form. Now if we come to the next question. So N2H4. So N2H4 in this cases, N2H4 under H2O2 condition form diamide. This one. So now this will react. There is a two double bond. This one ipso double bond and this double bond, and this is the ipso one. So now there is a possibility that this ipso, which is sterically less hindered, react with this diamide. What happened in this cases? I'm writing this way. So this will cleaning this one first. This dimethyl, dimethyl. So after NPH4 in presence of H2 to form this diamide, now this less hindered ipso double bond will react with the diamide H and such as 4 plus 2 fashion. So this will react here, this will react here and eliminate the nitrogen. Nitrogen will eliminate, will give what happens there? Hydrogen, one hydrogen is coming, second hydrogen is coming. So this is forming this product. So the ipso double bond, which is less substituted or less sterically hindered, hydrogenated in presence of N2H4 H2O2. This is diamide. So this is diamide reduction. Now the next question is this one. So this under Boden, what happened? H, B, boron, trigonal planar, we all know, OH, OH, methyl. So as boron is Lewis acid, oxygen is Lewis base or basic in nature, so it has lone pair. So it reacts the vacant p orbital of the boron from the Lewis acid base adduct, or if we compare the so between nitrogen and oxygen, if we compare the nitrogen is more basic, so it should react fast with the boron center. Then it will form this one. A which is methyl minus NH plus. So now water will remove from the system and giving this model methyl OH OH PH 3. So now this will as now boron is also diagonal pair, it has a vacant orbital. This oxygen can also react and give this compound the methyl OH minus OH plus. Sorry, one carbon is missing. pH, OH plus. Now minus elimination of water. So from this OH and this hydrogen, eliminate as water, giving pH, pH. So this is the active catalyst of Corey-Coxey-Shibata reduction. So this will form. So this is the active catalyst of Corey-Coxey-Shibata reduction. So under this kind of amino alcohol and boron, this kind of Corey-Coxey-Shibata active catalyst could be formed. So the right answer is this one. Now the last question is this. So under divalent reduction condition, what happened? So two equivalent of dival is used at minus, not minus high temperature. So we I previously discussed that any kind of nitrile group, any kind of nitrile under one equivalent of dival is aluminum, isobutyl, hydrogen. So the nitrogen lone pair will activate the aluminum as aluminum behave as a Lewis acid. So and this will prop and then will transfer nitrogen aluminum isobutyl isobutyl. So it I told that at minus 78 degrees centigrade, this complex is stabilized. This will Lewis acid base pair complex is stabilized. Now under water treatment, this giving aldehyde. So the imine is hydrolyzed. Now what happened at high temperature? So what is possibility at high temperature is that under high temperature as we are using two equivalent of dimer. So aluminum isobutyl hydride. So now this hydride will further reduce this in imine and give this one at high temperature. So this will further reduce hydride, hydride and so that negative charge will form after reaction isobutyl. Now this will extract proton from the system and give this one. And after the workup or water treatment, it will give this one. So this happen only in high temperature in presence of two more than one equivalent, more than one equivalent of divalent. So nitrile group under one equivalent of divinyl at low temperature form aldehyde. Same nitrile group under two equivalent of divinyl at a high temperature such as 110 degrees centigrade. This cyano group or nitrile group completely reduced to amine. So the mechanism I have discussed. So that is for today. Thank you for your cooperation. So if you have any question, you can discuss or ask me. Okay. Bye bye.